Hello students, welcome to this lecture on the subthreshold leakage part. So power, when we talk about the power, it is only about, it's not only about the dynamic power or the switching power, but it is also about the static power. And I think in this module and in the subsequent modules, we will cover this particular aspect of the power, which is also an important characteristics while we design the digital circuits. So static power, as the name suggests, it is basically when the circuit is in a steady state conditions, and we assume that when we develop the circuit in a CMOS using the CMOS family of logic circuits, once the output voltage reaches a steady state value, there won't be any power. But that's not the case. There will be some kind of a leakage current that will be coming from either from the junction, the body to the diffusion node junctions, or there will be a subthreshold leakage current, that is nothing but the leakage current which will be flowing from the drain to the source side, even when the circuit is in a steady state. There is one more, the leakage current that will be flowing from the gate to the body, or gate to the source side. That is also called as gate leakage current. So there are basically three aspects of the leakage current, and then once we have the leakage current, there will be a voltage drop across the transistor. Current multiplied by the voltage will give us a power, and this particular power associated with the leakage currents, with all the three components of the leakage currents, is termed as the static power. Right. So what we will do is, in this particular set of lectures, is try to understand the components of the leakage current. And we will look into the two important aspects of the leakage current. One is the subthreshold leakage current, which we will start in this particular lecture. And then subsequently, we will have a look into the gate leakage current. The junction leakage currents are a factor less than that of these two leakage currents, and hence we are not going to look into the junction leakage currents, but we will emphasize more on the subthreshold leakage current and the gate leakage currents. So moving on, so let me also take the pointer. Right. So I have I've written an expression of the subthreshold leakage current. So this is an empirical expression. That means after carrying out several experiments, an empirical expressions, or an expression to fit that particular experimental records or the data, this particular expression has been derived. And this is, it's an exponential expression. And then there is one more exponential term here. There are a lot of, the voltage references. The VGS, as we know, it is the gate to source voltage. VT0 is nothing but the threshold voltage. It's an absolute threshold voltage. VSB is the source to body voltage. VDS is again the drain to source voltage. VT is the thermal voltage, which is nothing but KT by Q. So there are two parameters here, two constants here, which is one is K gamma and then another is eta. So this K gamma is nothing but the body effect, or the body effect coefficient, and eta is nothing but the drain induced barrier lowering coefficient, and we will have a look at it in the next slide. So one important aspect of this particular expression is the VT0. So if I use a typical VT value of 0.3 volts, I'll get some current. But generally in technology node files or the library files, we can select different VT based standard cell libraries. So if I use a higher VT, that means this particular VT0 should be higher. So it maybe we can choose a VT of 0.4. Or we can also choose a lower value of VT cells of 0.2 as well. So based on that, our subthreshold leakage current will change. Because this VT0, it's in the exponential term, so we will have an exponential increase or an exponential decrease in the subthreshold leakage current. So if I choose a higher VT here, that means this difference between VGS minus this VT will be lower, and thereby my subthreshold leakage current will be lower. Right, so this is I subthreshold will be lower. And if I choose a lower VT, so lower VT will give me VGS minus VT0 to be higher, An exponential to that of the higher value will always give me a subthreshold increase in the subthreshold leakage current. So the I sub will be higher, right? So what we really want is to have a lower, the subthreshold leakage current. So in that sense, we'll have to use a higher VT. But there is one problem there. So if I look into the so the driving factor or the current that is there to charge the capacitance or charge the output node or discharge the output node. So the current, the long channel current. If I consider the long channel current and let me pick a saturation current. Right, so in that sense, it is nothing but beta n, and then I will write VGS minus VT the whole square. Of course, there is a 2 term here, so it is VGS minus VT the whole square. Now, if I choose a higher VT here, right? So if I higher VT, VGS minus VT is going to be less, and the current, the long channel current, saturation current is likely to be dropped. And this will have an effect. A lower drop in the current is likely to have a lower charging or discharging effect, and thereby the delay is likely to be increased. Right? So a higher VT is likely to give me a reduced subthreshold leakage current and thereby a reduced static power, but it will have an effect in the performance, in the overall performance. And whereas similarly, if I choose a lower VT, here, the current is going to be better, it's going to be higher, and my delay is going to be much less. So it is likely to give me an improved performance, but my subthreshold leakage current is going to be higher. Again, there is a compromise here. There is one, if we have to cater to one aspect, the other aspect tends to be tends to lag, or we have to compromise on the other aspect. So in that sense, there is always a trade-off, and based on the design requirements, one will choose the VT cells. Okay. Now this particular expression turns out to be a little bit complex in applying for the circuits, for the digital circuits, and then try to analyze the circuits in terms of the subthreshold leakage current or to evaluate the static power. So a better or an approximate equation has been stated, and that is this particular expression, whatever I have mentioned here. So I sub is nothing but I of, and then it is given in terms of, instead of an exponential term here, E term, it is nothing but 10 raised to 10 power term with the expressions of VGS, VDS, VDD, and VSB is given here. And then there is another term here S, which is nothing but the subthreshold leakage slope, and I'll come to that in the next slide. And then eta is still the same DIBL coefficient, which is nothing but the drain induced barrier lowering, and K gamma is nothing but the body the source to body coefficient, or the source to body effect coefficient. And the similar terms VDS, VSB, VDD, VDD is nothing but the real voltage, VGS, the gate to source voltage, everything remains the same. I of is one of the component which we will come in the next slide, which I'll explain in the next slide. So hope this is clear. Moving on, so this is what the expression we are going to use to analyze the circuit towards the static power, or towards the subthreshold leakage current. So let's have a detailed look at it. K gamma, what I said was the body effect coefficient. So and it is given by 0.066. So what it really means is if the VSB increases by 1 volt, the source to body voltage increases by 1 volt, I will have a K gamma effect of 0.066. So in fact, if you remember, if the VSB value increases by 1 volts, the K gamma is going to have an increase of 0.066 volts. So that will have an improvement in, that will have an increase in the VT of 66 millivolts. An increase in the VT is likely to have, an increase in the VT is likely to have the decrease in the subthreshold current, as well as the decrease in the overall long channel saturation current or the linear current. Right, so that effect has been incorporated. So this particular effect, K gamma effect, has been incorporated directly into the subthreshold leakage current. All right. So instead of going by an increase in the VSB, we'll have an increase in the VT, and then that VT component, the threshold voltage component, is then instead of putting it here, we have directly accommodated K gamma into VSB in the sub-threshold leakage current. Let's have a look at the eta. Eta is nothing but the DIBL coefficient, the drain induced barrier lowering, which is nothing but 100 millivolts per volt for the 65 nanometer technology node. Again, these constants K gamma, S or eta, it's all are all the empirical constants arrived from for a particular technology node. So if I consider the eta here, it is nothing but 100 millivolts per volt. So what it means is, if I change the VDS value by 1 volts, right, I will have a drain induced barrier lowering. So the channel is likely to be reduced. So the reduced channel is actually have an effect on the current, on both the currents, right, on the dynamic current as well as on the static or the subthreshold leakage current. So this particular subthreshold leakage current, if I have an increase in the eta here, if I have an increase in the, or rather if I have 100 millivolts per volt, if that is the constant here, if there is an increase in the VDS, I will have it, the effect in the channel, and thereby the subthreshold leakage current is likely to be affected. So that has been incorporated in this particular approximate equation in the form of the eta, right? So the eta we will consider for most of our calculation, we will consider it to be 0.1, which is nothing but 100 millivolts per volt. So 0.1 volt per volt. K gamma is given as 0.066 as a constant. The last one is the subthreshold slope, and that is 100 millivolts per decade. So let me try to draw a figure here in the side by. So what it really means is, if I draw the current versus it could be a dynamic current. So I'm drawing a current of the transistor. I'm drawing, in fact, a current of drain to source, and I'm not doing any kind of a partition or a classification between whether it's a static current or it's a dynamic current. So I'm just drawing a current across the VGS voltage, right? What we knew at before was at 0.3 voltage. At 0.3 voltage, I will get some minimal current, and then at 0.4 voltage, I'll get a higher current, and then so on. 0.5 voltage will be higher current, and then so on, right? So at somewhere here, we said at 0.3 volts, that is when the channel will be formed, right? The channel will be formed, and then after the channel is formed, then I'll get some amount of current based on the VDS value, and if the VDS value is more than the VGS minus VT, I'll get the saturation current. So that's what we used to say, right? So let's say that the transistor is in saturation, and then I'll get some some current here, and it will be VGS minus VT the whole square. So I should have a square relationship, and these are those points, right? Note that here at 0.3 volts, right, I've drawn a non-zero current. So this will be a non-zero current, this particular point. It's a non-zero current, right? But it will be very, very close to the zero current. So what it really means is, if these currents are in the range of, milliamperes, I'll get some kind of a current here in the range of microamperes. But there will be some current. There will be some non-zero microamperes of current, right? And if I go back to 0.2 volts and then 0.1 volts, right, we used to say that the channel is not at all there, and then there won't be any current at all. But that's not the case, right? There will exist some kind of a channel, right, where the drain to source will still be having some negligible amount of current, and that is called as the subthreshold leakage current, right? And that particular current is, I can point it out in the form of the dots. All right. This particular slope, the slope in the subthreshold region, that is below 0.3 volts for our typical VT values. So if I draw this particular line, so I will get I can have some kind of a linear line if I consider it for a decade change in the current, right? So I will have some kind of a slope here. So what this slope says is, this is this subthreshold slope S, and that that has been characterized in a way that if I change my VGS value for 0.1 volts, right, if I change my the voltage values in terms of 0.1 volts, right, I will get, so 0.1 volts means 100 millivolts, I will get a decayed change in the current. So I'll get a decayed change in the current, so a decayed change in the current. So what it means is if it is at 0.3 volts, let's say my current, right, I'm going to say that IDS, or rather, subthreshold current. Let's say that the subthreshold current is 100 microamperes. At 0.2 volts, the same current, we will be having a decayed change in the current. So I will have at 10 microamperes. At 0.1 volts, I will have the I subthreshold current as 1 microamperes. So I will see a decayed change in the current, and that is what the slope says here. So the slope indicates that the change in the current with respect to the change in the voltage, and that is what is incorporated here. And we will use this in our approximate subthreshold leakage current equations. Right? So hope this is clear. All the three terms K, gamma, S and N are clear. So S, we will consider it to be 0.1 because it is 100 millivolts per decade, and we will consider it to be 0.1. So this eta is 0.1, K gamma is nothing but 0.066. Right? Hope this is clear. So let's take a single transistor here, and I'll come to that I off value, or rather, in fact, I'll just define that. So I off is stated as nothing but I sub. I off is nothing but I sub at VGS of 0 volts and VDS of 1 volts, or rather VDD rail, and VSB is 0. So basically in an ideal transistor where I have the drain to source potential as VDD rail or VDD, and there is no body effect, so VSB is 0, and let's say that at the gate side there is a 0 volts, then I'll get whatever is the current. Right, that particular current is the I sub, or rather whatever is the subthreshold leakage current, that is nothing but I off. So this is basically, this particular term is nothing but the subthreshold leakage current when the transistor is completely off. Right, so let's move ahead into this particular transistor, analyze this particular single transistor, and then try to find out the subthreshold leakage current. So in this particular aspect, in this particular transistor of an NMOS, we have this VDS as VDD, the VGS as 0. So if I put it in this particular expression of 10 raised to VGS, VGS is anyways, 0. Eta, we know that it is 0.1, subthreshold is 0.1, K gamma is 0.066, VDS in this case, it is nothing but, VDD. And VSB, it is, we will consider it to be 0 if it is not given, right? Or if it is not given, we will anyways assume the body for an NMOS transistor to be connected to the ground and body of the PMOS transistor to be connected to the VDD, right? So in that sense, VSB will be 0. So if I have all these components, all the numerator will be 0. So I'll be left with I sub is equal to I off. So indeed, our definition of I off, which is nothing but I sub, when the transistor is off, completely off, that means the VGS is 0, is indeed correct, right? So I'll also like to reiterate here what, at a cross-sectional level, when I draw the NMOS transistor, what we used to say is I had a diffusion pockets, right? And this is the oxide, and then this is the gate. What we used to say is whenever, this is the gate to source. So this is my source, this is my drain, and let's say that I have some potential here, drain to source, and then some potential here, gate to source. So we used to say that VGS, only when it is greater than 0.3 volts, I will have the channel. So I will have some channel here. And if VGS is smaller than 0.3 volts, there won't be channel. So I said there is a no channel, which is incorrect, right? We cannot have this kind of a demarcation in a transistor. Now the channel will appear and then channel will disappear at 0.3 volts. If it is greater than, at 0.3 volts, I will have a channel. And if I have 0.29 volts, 0.299 volts, I will not have a channel. So that is kind of a slight approximation which we had done to find out this channel and then the current through the channel, and which is generally in the range of hundreds of microamperes to milliamperes. But when the channel is not there, that is when when the VGS value is in the below 0.3, that is, it is below the threshold voltage, also called as the subthreshold region, we will still have some kind of a current. We will still have some kind of a current that will be flowing from the drain to source, right? So this, we call it as the subthreshold leakage current. And what we had seen here is, using this particular expression of the approximate equation, we should be able to find out, given the values of VGS, given the value of VDS, given the VSB value, using these constants, right, the etas, the k gammas, and then the subthreshold slope, we should be able to find out the subthreshold leakage current for the transistors. Right, hope this is clear. Moving on. So let's say that if I have two series of transistors, right, so there are two series of transistors and both of them are off. That means it is not above the threshold. So the VGS for this transistor 1 and VGS for the second transistor, both of them are below 0.3. So we will have, it is already in the subthreshold region, and then we should be able to calculate what is the subthreshold current, right, using this particular expression. So if I say that this is transistor 1 and 2, I need to find out what is VGS. VGS turns out to be, if I write this particular internode voltage as Vx, this particular VGS value is nothing but minus of Vx. VDS turns out to be VDD minus Vx. For the second transistor, VGS is 0. Or for the second transistor, VDS is nothing but Vx. And if I put those particular parameters into this subthreshold current, and because these two transistors are in series, I know that in the series, the currents, even the subthreshold leakage current, will be the same. So I should be able to find out I sub 1, I should be able to find out I sub 2, or rather express this I sub 1 and I sub 2 and then equate it. Then I should be able to find out this particular node voltage, right? Now to express I sub, the subthreshold leakage current for transistor 1 and then subthreshold leakage current for transistor 2, I will use this approximate equation where VGS for the transistor 1 is nothing but minus Vx. VDS is nothing but for transistor 1 is VDD minus Vx. So this term of VDS minus VDD will turn out to be minus of Vx. And VSB turns out to be source is Vx and body is connected to the ground. So we will have it as Vx. And for the second transistor, the VGS is 0 and VDS is Vx. So this term will be Vx minus VDD. And VSB is, the source is 0 and then the body is also 0. So we will have it as 0. So I will have these two expressions, expression number 1 and expression number 2. And if I want to equate this two, so that I should be able to find out the Vx values, right? So we know that this current and this current are equal and I off is also equal. So I can, cancel this on both the sides. And if I take the log on both the sides, I should be having only the expressions in terms of Vx on the numerator and denominator side, and then similarly here. So I should be able to equate this particular expression with that of this particular expression, because the transistors are in series, because the subthreshold leakage currents are same, right? So we should be able to find out Vx in that case, which turns out to be 0.0789 voltages. And it makes sense because both the transistors are off, so I will have a very, very minute amount of the leakage current in terms of microamperes or less than microamperes. And it is going to have, even if there is a steady state flow, steady flow of the leakage current coming from the VDD rail to the off transistor of transistor 1 and the second off transistor and then going to the ground. Because of this minute current, the voltage that is being developed, right, due to this minute current will be very, very small. So that will be 0.0789 volts. Once I have the Vx value, I should be able to find out the actual subthreshold leakage current. So the subthreshold leakage current, putting into that one of these equations of I sub 1 or I sub 2, I should be able to find out the current, which is nothing but 0.1199 I off current. The I off current is generally, for an off transistor, we say that it is kind of somewhere around 5.63 nanoamperes, right? For an NMOS transistor. So if I do that, it will be 0.5 nanoamperes, right? For a 65 nanometer technology, this is something we will use in the future slides. So the I subthreshold, the leakage current or the subthreshold leakage current, if I have two stacked transistors, which are in series, turns out to be I off by 10, approximately, right? So this is 0.1199. So if I can approximate it to 0.100, I'll get I off by 10. So stacking two transistors reduces the subthreshold leakage current significantly and to an effect that it brings down to almost 10%. Now, which is very, very nice. So if we have a way to reduce, if we have a design specifications to reduce the subthreshold leakage current, now we can always use a foot transistor, which is off, and the stacking of the transistor will help in reducing the subthreshold leakage current, the subthreshold leakage power, and directly it will have an impact on the static power. All right, hope this is clear. Moving ahead. So now what if I have three series transistors? In the last case, we had seen two of the transistors in series. Here now it is three transistors in series. So now I have to find out the node voltages Vx as well as the Vy, the two node voltages, right? So because the three transistors are in series, I will have the subthreshold leakage current to be the same. So I can write the subthreshold or express the subthreshold leakage currents in terms of this node voltages, right? Write the subthreshold leakage current for one transistor, for the second transistor and third transistor, and equate it, one with that of the third subthreshold, the subthreshold leakage current of the first and the third transistors will give me one equation here. And similarly, if I equate the subthreshold leakage current coming from the second and the third transistor, if I equate it, I should be able to find out the second equation, right? So if there are two equations and two unknown node voltages Vx and Vy, I should be able to calculate that. Putting this particular equation into the first one, we should be able to estimate the Vy and Vx. If looking at this particular values of Vy and Vx, it is 0.0006729 and Vx is 0.0851. So Vx is higher than that of Vy. And just to confirm our calculations, Vx is higher than Vy makes sense, because if I have a node voltage higher than the other one, then only I will have the current that will be flowing from the drain to source. So if it is the other way, then there is some problem in our equations solving or in our assumptions. So in this case, what we have assumed is the transistor 1, 2 and 3, there will be a current that will be flowing. And thereby, we identified Vx and Vy, and it turns out that the Vx potential is higher, slightly higher than that of Vy, and our assumption of the subthreshold leakage current that will be flowing from VDD to ground makes sense, right? So, and also notice that the Vx value and Vy value are in the sub voltage levels. So that means that it is either in the form of 0.0851 or it is 0.0006729 volts. So it's actually very, very low, again, which brings to our attention that the subthreshold leakage current is actually very, very minute, right? Very, very low compared to our, the dynamic current or the transient current, which we will estimate which we generally use it to estimate the delay and the power in the dynamic power characteristics. Right. So in that sense, the subthreshold leakage current, if I know the node voltages, I can put it back into those the subthreshold leakage current expressions and find out the overall current, the subthreshold current, which turns out to be 0.101. Right. It is even lesser than when we had the two stacked transistor, which was 0.1199. So it is actually coming very, very close to the 10%. So 0.101, which is lower than 0.1199 of I off. So stacking more transistors decreases the subthreshold leakage current. So if I have four transistors stacked together, the subthreshold leakage current is naturally going to be reduced, right? Compared to the 3 series transistors and the 2 series transistors. Right? Hope this is clear. Going forward, so let's take the question is where are we going to use this stacking effect, and how do we use those stacked transistors in our evaluation of the static power. So if I consider the 3-input NAND gate and with a logic of 0, 1, 1, right? So, and I'm looking at the pull down circuit. If it is the logic is 0, 1, 1, we know that the output will be 1. So that means that the pull up circuit will be on, and the pull up circuit, the PMOS transistor is going to ensure that the output is charged to the VDD value. right? So the output is charged to VDD value here. And in 0, 1, 1, I know that if it is 0, this transistor number 1 will be off. So it will be in subthreshold region. So that means it should drive the subthreshold leakage current. The second and third transistor, although this is on, because this transistor is off, right? So it will have to, if this supplies the subthreshold leakage current, this is going to take this, the supply of the subthreshold leakage current and then put it into the ground, right? Now to analyze what should be the subthreshold leakage current in this particular case, we can consider this particular transistor and then this particular on transistor, so both the on transistors, to behave like a pass transistor. So the reason is, if this is connected to the ground and if I have a capacitance here, all right, this capacitance, because this is grounded and because this is on, this is anyways going to get discharged to the ground. So my Vy voltage will always be 0, right? And similarly, if I consider this, there is a capacitance here. So C3 and C2 I will write. So the C2 capacitance is also will, because this is an on transistor and we can consider it to be a pass transistor. So C2 capacitance, whatever value it will be charged, there is a path, there is a discharging path from this on transistor, from this on NMOS transistor, and the on another NMOS transistor, which will get connected to the ground. So my Vx value can also be considered to be 0. Now the question is, what should be the subthreshold leakage current? The subthreshold leakage current will be, estimated by this off transistor. Now with these three transistors, we can consider it to be an equivalent of one single transistor, one single off transistor, where one node voltage is connected to VDD, because this is kind of driven by the pull-up circuit for the 3-input NAND gate. And on the other side, the Vx is actually 0 volts. So my I subthreshold leakage current is nothing but I off. So this will be the subthreshold leakage current, which will help, which is going through all the three transistors, right? And the I subthreshold leakage current for the transistor 2 and transistor 3 is going to, help in complete discharge of the C2, the diffusion capacitances of the C2 and C3. Right? Hope this is clear. Moving ahead. What if I have a logic of 1, 0, 0? Again, the output, if the logic is 1, 0, 0, so the output will be 1. That means that the pull-up part of this 3-input NAND gate will be active and will be driving this output node voltage to VDD. So if I have 1, 0, 0 here, right, so these are off transistors. So this is going to determine the subthreshold leakage current, and this is an on transistor, right? So the subthreshold leakage current is this one and this one, which will be determined by these two off transistors. This one being an on transistor, and if Y is held at VDD, I can consider it to be a pass transistor, and the other side of the node, right, will be charged to VDD minus VT, right? And if I can actually make these three transistors into two off transistors, where one side it is VDD minus VT, on the other side it is grounded, the two off transistors and both the off transistors are in series. So the subthreshold leakage current of this transistor and this transistor should be same. So we should be able to use this VDD minus VT, use this Vx value in the subthreshold leakage current, equate the subthreshold leakage for the first transistor and then the second transistor, equate it out, and we should be able to find the Vx value, right? Turns out to be 0.05529. The subthreshold leakage current turns out to be 0.1135 of the I off, right? So if I have a VDD minus VT on one side and then two stacked transistor and then a ground, then this Vx value turns out to be slightly lower. The reason is the subthreshold leakage current is slightly lower than our 0.1199 I off, right? When the two transistors were stacked on, and one side it was the rail voltage of VDD, on the other side it was ground. Here, because of the third transistor, we are having this particular node as VDD minus VT. Right, so in that sense, because of the slightly lower voltage here, my current is slightly decreased from 0.1199, it has been decreased to 0.1135. Also makes sense because the voltage is slightly less and thereby the current should be slightly less. Right, so my subthreshold leakage current for the two stacked transistors If I see if I see a voltage of VDD minus VD on one side and the ground on the other side, I will get 0.1135 of the I of current.